Welcome back. We are studying numerical linear algebra, and we started by uh, a method to solve a homogeneous system of linear equations. This is the method proposed by Carl Friedrich Gauss, and so it's called Gaussian elimination method. We are going to learn that method further. We saw that there is a slight problem if that diagonal entry is 0 at every step, at the ith step. So we need to see what to do if that particular entry is 0. And of course, there are ways to go around with that. I hope you can now see the slides. Okay. All right. So we are interested in solving the linear system, the system of linear equations. This is the system a matrix n by n matrix into a column matrix of the variables equal to a column matrix of the entries. So this is written as A dot x equal to B, and we want to solve for the matrix X using the A and B, which have real entries. As we have noted already, this system has a unique solution if the matrix A is invertible. And of course, you know this from your linear algebra course that this is true if and only if the determinant of the matrix is non-zero. How do we apply Gaussian elimination method? This is applied to make your matrix A an upper triangular matrix. We will transform the matrix A to an upper triangular matrix so that then the system can be solved quite easily. So once you make it upper triangular, this is how the system will look. And then we can solve first of all for xn using the last equation. You have to just divide by a and n, and that will give you the value of xn. Once xn is found, we will use it in the second last equation, which is this: a n minus 1 n minus 1 x n minus 1 plus a n n xn equal to b n minus 1. This is the last but one equation. And now here we have found the value of xn. We plug that value, compute this particular product, and subtract it from b n minus 1 to get the a n minus 1 n minus 1 x n minus 1, and then divide by a n minus 1 a n minus 1 to get the value for xn. Okay, the procedure is going to fail if the element ai is 0. The way we have defined the procedure, this is going to fail if some diagonal entry ai happens to be 0 after having cleared the variables x1 up to xi minus 1 from the ei onwards. Okay, so we will first clear x1 from e2 onwards. Then e2 onwards we look, that will have x2 up to xn variables. So using the a22, we would want to eliminate x2 from e3 up to en. And so we continue. So if you have eliminated x1, x2, xi minus 1 from the equations ei plus 1 up to en, after that we want to eliminate ei. But to do that, we need aii to be non-zero. If this aii is 0, then what do we do? Because this particular operation then cannot be performed if your aii is 0. The system may still have a solution. It's not that we are saying that the system doesn't have a solution. The system may still have a solution, but we will have to alter the technique of finding it. We will have to get a new way to solve this system. So let's understand this through one particular example. So suppose I have this particular system: 1 minus 1 2, 2 minus 2 3, and 1 1 1. This is multiplied to x1 x2 x3 to get minus 6 minus 14 0. Now we want to eliminate x1, so we have to do something to e2 e3 depending on e1. So we do e2 minus 2 e1 to e2, and e3 minus e1 to e3. This is what we are going to do. So once you subtract twice of e1 from e2, you see that this is 2, this is 1. So 2 minus 2 of 1, that gives you 0. This is minus 2. This is minus 1. So if I multiply minus 1 by 2, that gives me minus 2, and subtract it from this minus 2, I'm going to get 0 here also. The highlighted entry also becomes 0. So what I get here is 0, 0, and the last one will change because I am subtracting twice of minus 2. So last one will become minus 1. So it is 0, 0, minus 1. And this entry minus 14, because I will multiply to minus 6 by 2, it is minus 12. That is to be subtracted from minus 14. So I will have to add 12 to minus 14 and I get minus 2. Okay, so it's going to be 0, 0, 1 and minus 2. Now let's look at the last row. We are simply subtracting E1 from E3. So it will give me 0, 2, minus 1. And this will become 6 because you are subtracting E1. So it gives you 6. So this is what we are going to get. We get 1, minus 1, 2, x1 and minus 6. The first equation remains as it is. The second equation has become very simple. In fact, it has become 0, 0, minus 1 into x1, x2, x3 equal to minus 2. And finally, we have 0, 2, minus 1 into x1, x2, x3 is 6. So here this a22 is now 0. We cannot perform the next step. But we notice that there is one non-zero entry in the same column below the 0. We are not going to touch E1 because E1 is now set. We are all right with E1. We are not going to disturb that. We have to only work from E2 and below E2. So we notice that in this second column already, there is a non-zero entry below the 0, which is A32. So we perform the operation of switching these two rows. So by switching these two rows, this 0, 2, minus 1 has gone to the second row, and 0, 0, 1 has come as the last row. And this 0, 2 and 6, they are also interchanged, 6 and minus 2. Minus 2 and 6 are interchanged as 6 and minus 2. We are not disturbing the variable x. You know, to understand this, we have to note one thing which we are going to talk about when we talk about LU decomposition, which is that all these operations are effected by multiplying to your system on the left by some matrix. So we are going to put some matrix B here. It will have to be put on the final B, small b also, because if you want to maintain the equality, you have to multiply both sides by the same matrix, and therefore if the matrix change gives you a switching of two rows, that same change will have to happen on the equation, that B column also, but the X column remains unchanged. Okay, so once we have obtained this particular system, then we can solve it easily. X3 is 2, X2 is 4, and X1 is minus 6. So this is what we have done, and let's put it back in the algorithm. So the above example will illustrate what needs to be done if your AKK is 0 for some K. What needs to be done is that we search for first non-zero entry below AKK in the kth column. So we look at the kth column from AKK onwards. So it will be AKK, AK plus 1, comma K, AK plus 2, comma K, all the way up to A and K. The second subscript will remain the same because you are looking at the same column. Okay. Suppose there is one APK, which is non-zero for a P between K plus 1 and N. Okay. So there is some such which is non-zero. Then we are going to switch the rows EK and EP. Now what is happening is that EK and EP, these are both the rows which are below the K minus 1th row. And therefore, by induction hypothesis, we have made all the entries in these rows from 1 up to K minus 1 zeros. So the variables x1, x2, k minus 1 are all eliminated from K onwards. Therefore, even if you switch the EK and EP, the first number of zeros, which is K minus 1 for both of these, that is going to be the same. And then you have this new EK, which has its first entry kth entry to be non-zero, and now you can continue the procedure. The procedure then can be continued. So this is the way we will work. We will work with A11. If A11 happens to be 0, then we have to switch some row and put it back in the place of E1 to get the first entry non-zero. And then you effect the elimination of the variable x1. Now look at E2 onwards. If the A22 is 0, again switch some row and get the second entry of the second row non-zero, and the procedure can then be continued. Of course, you may ask, what will happen if all these entries are 0? If this is the case, then the matrix will not be invertible. For instance, if you are looking at the first entry itself, and you notice that your first entry A11 is 0, and after A11 all the other entries are also 0, then your first column is 0. Then in that case the matrix is not invertible. This is in a essential sense, this is what happens when you are looking at the kth diagonal entry and below that also, because you have zeros up to k minus 1 in the rows from ek onwards. If your kth column also happens to be 0, then you have a scale, then you will eventually have that the determinant of the matrix is 0, and therefore the matrix is not invertible. Then of course the system is not expected to have a unique solution. In fact, it doesn't have a unique solution, and so the procedure will then stop. Or you may have the final ANN might be 0. Below that you cannot progress. So if your ANN is 0, you have made the matrix upper triangular, and so the determinant is simply the product of the diagonal entries, and among them the last one is 0, then of course the matrix is not invertible. The linear system doesn't have a unique solution. Again, the procedure stops. So this is what one has to do. If your particular diagonal entry in the ith step is 0, you search for a non-zero entry in the same column but below that. And if you get one such, you switch these two rows and continue. This is how the whole Gaussian elimination method works. Now, what we want to do is to count the number of operations. So after learning this method, we are interested in finding the total number of arithmetic operations which are performed in the method. So this is what we will do when we are dealing with matrix operations, matrix related methods, that we would want to compute the total number of operations. So in general, there are actually four types of operations. You have to do addition, you have to do subtraction, you have to do multiplication, and you have to do division. So the addition and subtraction are similar in nature. Multiplication is slightly more complicated because it is a complicated form of addition, and division is even more complicated. But what happens is that on a computer, the time required to perform a multiplication or a division is approximately the same. Okay, but it is considerably greater than that required to perform an addition or subtraction. So among these four operations that we will be doing, addition, subtraction, multiplication and division, the multiplication and division have to be computed separately. Those ones will be counted separately together, but it has to be separate than the addition and subtraction. How much difference will the time be? That will of course depend on a particular computing system. If you have a very fast computer, it will compute all these operations in a jiffy. Okay, so however, to demonstrate the counting operations in a given method, we will count the operations required. So this is what we will have to do, but we will count the addition and subtraction separately together, and multiplication and division separately together, and we will see this how to do it in the example using the Gaussian elimination method. And the count of addition and subtraction, I'm emphasizing this again, is going to be kept separate than the count for multiplications and division, because the times are different, and depending on your machine, the difference can be seen. Okay, so we are applying first of all, so the method consists of making your matrix upper triangular and then doing the backward substitution. So if you assume for the ith step that x1 up to xi minus 1 have been eliminated, then we want to eliminate xi from ei plus 1 onwards. So we are going to define this mji, which is aji upon aii, and we will perform this particular operation. Okay. So here n minus 1 divisions are performed because you want to compute mji. This is done for j equal to I plus 1 up to n. So these are n minus 1 divisions. Then for a fixed j, the mji is multiplied to each term of ei. How many terms does ei have? From ei, x1 up to xi minus 1 have been eliminated. So ei has xi term, xi plus 1 term, and so on. So there are n minus I plus 1 terms in the ei. And we will multiply these n minus I because you are going to multiply the mji to ei for each j, right? So for each j, I should have put this ej. This is a mistake. I should have put this ej here. Your row ej is going to change. So for each ej, you will multiply by mji to the n minus I plus 1 entries of ei. And this you are going to do for each j. So the total number of multiplications in the ith step is n minus I into n minus I plus 1. Then each term of the resulting equation is subtracted from the equation ej. So after having computed this particular equation mji, we now need to subtract it from ej, and once again the subtraction will have these many operations because the subtractions are these many, n minus I plus 1, and they have to be done for each j, which are n minus I in number. So these are the total subtractions, and therefore the multiplications or divisions, that number is this. You have the n minus I to begin with, and you have these n minus I plus n minus I plus 1. So the total number of multiplication or division operations is n minus I into n minus I plus 2. At each step, this is the number of multiplication or division operations, and addition or subtraction is simply n minus I into n minus I plus 1. Okay, so n minus I into n minus I plus 2, these many multiplications or divisions, and n minus I into n minus I plus 1, these many additions or subtractions. Now some of these can be 0, so you may wonder if some of these are 0, then do we have to do this? But this is the computer operations that we are looking at, so even the 0 will have to be counted, although the answer will be 0, of course. All right, so now we have to do the total number of operations required for this, and this is going to be done for, now we will do it from x1, x2, x3 up to xn minus 1. The last variable will not be eliminated because there is no equation after the nth row. So the multiplication or division will be I going from 1 to n minus 1. You have to do it for only n minus 1 times. N minus I into n minus I plus 2. So this you can see we have n minus I, and you multiply by n minus I, you get n minus I square, and then you have 2 times n minus I. So I will separate these two summations. I have I going from 1 to n minus 1, n minus I whole square, plus 2 times I going from 1 to n minus 1, n minus I. But as you are going from 1 to n minus 1, n minus I goes from n minus 1 to 1. So these are the same sums. Either you take these n minus I or you just take the I. Those are going to give you the same numbers ultimately when you are summing them. So this is just I going from 1 to n minus 1 I square plus 2 times I going from 1 to n minus 1 I. You know how to compute these summation formulae, or if you don't know, you can prove them by induction. And this is the final answer: 2n cube plus 3n square minus 5n upon 6. This is the total number of multiplication and division operations while making the matrix upper triangular. Okay, we have to still count the number of additions and subtractions. So additions or subtractions, that number is given by 2 replaced by 1. So we do the same way. We separate out n minus I square and n minus I. We again observe that it is just summing I square and summing I. So we get n minus 1, n 2n minus 1 upon 6 plus n minus 1 by 2. It's only going up to I minus n minus 1. And then the final answer is n cube minus n upon 3. So this is the count of addition and subtraction operations. So these two have been used to make the matrix upper triangular. Now we have to do the backward substitution. So the computations, the number of operations required in the backward substitutions, they will be counted. Each such step will require n minus I multiplications. So assume that you are looking at the EI, which has entries from xi plus 1 up to xn, and there you would want to compute the variable xi. So there are en minus I multiplications. This is because you have computed the variables xn minus 1 up to xn minus I plus 1. So you have to ignore the ith variable is still there, xi, but we have not computed the xith entry, right? We have computed xi plus 1 up to xn. So ignore the first I and xi plus 1 up to xn. Those are the n minus 1 entries which you have computed. You will multiply those to the corresponding coefficients, and therefore you have n minus I multiplications. Then there are summations, n minus I minus 1 additions per summation term. You have to add those. And when you have 2 entries, you have to sum them once. Then you have 3 entries, you will sum them. There will be 2 summation operations. So for n minus I entries, the total number of additions is n minus I minus 1. Okay, so that will give you the sum, and then you subtract it from the BI. So that is one subtraction. And once you have done that, you will divide by AII. Finally, one division. This is the total number of operations when you are doing it per step in the backward substitution. So let's count it again. Now, this we will have to do for all the n equations, because you have to count, you have to compute all the variables x1, x2, x2 up to xn. This, for the last xn part, it's only one division. There is no previous addition, subtraction and all those things. So that one is kept separately. And then you are doing it for n minus 1, n minus 2 up to the first equation. So those are taken here together. Okay, that's what we have done. So this is 1 plus the n minus I. You have to just sum them. And 1 being summed from 1 to n minus 1 gives you n minus 1. So this n minus 1 plus this one will give you n. And you have to sum the n minus I from I equal to 1 to n minus 1. That is just summing like, that's just summing I. And this is the final answer, n square plus n by 2. These are the multiplication or division operations in the backward substitution. The addition, remember there is n minus 1 minus 1 subtraction additions, and then there is a subtraction. So that 1 gets cancelled. So the number of additions and subtraction is just summation I going from 1 to n minus 1, n minus I, which is also summation I, which we know is n square minus n by 2. So now we are going to add all these. You started with your matrix A, you made it an upper triangular matrix. So that number of operations of multiplication and division as well as the addition subtraction, they will be added to the corresponding number of operations in the backward substitutions. So the total number of operations for multiplication and division, remember you had it 2n cube plus 3n square minus 5n by 6 for the making the matrix upper triangular, and n square plus n by 2 for the backward substitution. That gives you this as your final number. The addition and subtraction similarly can be computed to be this. So we see that the n cube plus 3, n cube upon 3, that is the dominating term. It's going to be a polynomial in n, that is not surprising, but this is the dominating term. So for large n, the total number of multiplications and divisions is approximately n cube by 3. The other terms will fade away. As your n goes bigger and bigger, the contribution will be more and more from n cube by 3. The same as that for additions and subtractions. Therefore, the amount of computation and the time required for n will increase in proportion of n cube. Roughly, it will not happen for everything, but it will increase in that way. So for instance, we will just compute a few. If you had n equal to 3 and you put the values in that formula, you will see that there are 17 multiplications or divisions required, whereas there are only 11 additions or subtractions. If you go to 10, the number becomes 430 and 375. For 50, it is 44,150 for multiplication or division. And for addition or subtraction, it is 42,875. And finally, for 100, so if you have a 100 by 100 matrix, then you will have to compute 3,43,400 operations of multiplication or division and 3,38,250 operations of addition or subtraction. So we see that roughly for the n, so for instance, if you take 100, the cube of 100 will be 1 followed by 6 zeros, which is roughly 10 lakh. And the number we are getting for multiplication or division as well as for addition and subtraction is roughly 3,33,333, which is the 10 lakh divided by 3. And this equality, the approximate value, will become more and more closer as you go on increasing your n. For instance, if you are taking n equal to 10, then you see that this is only 430. It's not really 333. And this is only 375. 10 cube is 1000. 1000 divided by 3 is 333, roughly. That's not what this number is, because there are other entries in the formula also, but those entries will become smaller. They will become negligible as your n increases. So this is where we stop in this lecture, and in the next lecture, we will see that we have to be very careful. We have been talking about these matrices with real entries, and so far what we have done is that we have done examples only with integer entries. But with real entries, we know that there are round off errors, and we have to be also careful about cancellation of two nearly equal numbers. So we will see how we can take care of such things in our next lecture. So see you until then. Thank you very much.